Okay, so our last topic would be about infeasible linear programs. Or say it in another way, given a linear program, we told you that if you have a lot of constraints, if you have a lot of variables, we don't even know whether it is feasible or infeasible. We need to have a way to check whether it is feasible or not. If it is infeasible, we want to find it. If it is feasible, we want to find an optimal solution. So that's our task here. So given a general linear program like this, if we have b that is non-negative, we know we may add slack variables into these constraints to get a standard form. This is trivial. And then there are some other issues. When we have only less than or equal to, everything is easy. Everything is easy. But if we have equality or greater than or equal to, that will create some other problems. For example, given a linear program like this, with some equality constraints, with some greater than or equal to constraints, according to our standard way to get a standard form, here for the second constraint, we don't need to do anything. For the first constraint, we need to minus a slack variable. And then this problem immediately gets non-trivial to find a feasible basis. Okay? Given any three columns as your basic columns, you really need to solve a 3x3 linear system to check whether the values are positive, 0 or negative, to check whether it is a basic feasible solution. Unlike in the previous case that when you only have less than or equal to variables, you add slack variables, and those slack variables immediately give you an identity matrix. That's easy. Today, you don't have an identity matrix, so that's why this problem is hard. Okay? So, there is at least one thing you may do. You say, oh, by default, there is no identity matrix. How about I artificially make one? Okay, let's see whether that idea works. So I'm going to do this. When I have a standard form linear program, I know in general that particular A probably does not contain an identity matrix. So I'm going to artificially add one. I'm going to create another LP which is called a phase 1 linear program, Q. Okay, I'm going to modify the constraint to give each constraint an additional artificial variable, y1, y2, y3, y4, blah, 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 blah. So I want to create an identity matrix by myself, so that later, if I say y is b, and x are zeros, then that's a feasible solution. Okay, so for this phase 1 linear program, finding a feasible solution is very easy because we have this identity matrix. And also, I want to do something so that this particular phase 1 linear program can help us know something about our original program. So what should I do? What I do is to minimize the sum of all the y variables. I know b are non-negative, okay? So typically some b are positive. So if I set y to be b, I would initially have a positive number here. And then if I try to minimize this particular system, I will try to push all the y's to be 0. If I can really do that, if the optimal solution for Q can have the objective value becomes 0, that means there is a feasible solution where x is something and all the y's are 0. Then that particular feasible solution obviously would be the feasible solution for P. Then we are done. We can say, oh, for the original problem, there is a feasible solution. Now, by carefully design our phase 1 LP's objective function. Or if you try your best to solve your phase 1 linear program, but you just cannot find any solution that can give you 0 as your objective function, then that means to satisfy this, some y must be positive. Then there is no way for you to satisfy ax equals b. Okay, so that's the idea. So that's something gives us proposition 1. Your P is feasible if and only if your Q has an optimal BFS which has all the y's 0. In that case, your x bar, which are the values of x in that particular case, would form a BFS of your P value or of your P linear program. So that's the key idea of defining or identifying the feasibility of a linear program is by solving another linear program, which is very interesting. Okay, so in general, what our plan is to have the two-phase implementation of a linear program or a two-phase implementation of our simplex method. We want to solve P, so the phase 1 is to solve Q to see whether P is infeasible or not. At the end of phase 1, we get a conclusion, and if possible, we get a basic feasible solution for P. And then we do phase 2 to keep iterating from that basic feasible solution, and then we get to unboundedness or an optimal solution. So phase 1 is for a feasible solution, and the phase 2 is for an optimal solution. Regarding those added variables, we call them artificial variables because we artificially make an identity matrix. And also, even though in the previous page we say we want to add y1, y2 up to ym for each row, but actually for less than or equal to constraints, if you prefer, you don't need to do that because there is already one slack variable there. Okay, so keep that in mind. You may want to do that. You may want to leave those less than or equal to constraints with no artificial variables to save you some time. And once we have the phase 1 problem, we then adjust our tableau according to the initial basis and then move to simplex method typically and up to phase 1 the end, and then phase 2, and then get to the conclusion. So it's example time. Suppose we have a linear program like this. Okay, there is a guy which has a greater than or equal to constraint. So that's why after we have a slack, we have an artificial variable here. We add this so that we can create an identity matrix for x4 and x5. And then whatever objective function we have, we don't care because now we focus on constraints to solve the feasibility problem. We modify the modify the objective function to be minimize the sum of artificial variables. Okay, so we now want to push x5 to be as small as possible. Now we want to solve this phase 1 linear program. And to solve this phase 1 linear program, let's do something to the initial tableau. Because if we just copy those numbers here, we see there is a problem. Because here, we want to choose x4 and x5 to be our basic variables. But this guy is not 0. That's not good. So we need to adjust the zeros row with elementary row operations. So that means we want to add row 1 into row 0 to fix the zeros row to get this. Okay, after the adjustment, then we have a valid tableau. So the right hand side one, this one is our initial tableau. Okay, x4 and x5, they are both 6. And that's why your objective value for phase 1 is 6, because your x5 is 6. Your current basic feasible solution is 00066, which corresponds to an infeasible solution to the original LP. if you take a look at these two values and plugging them into your original LP, that's not going to be feasible. Okay, so now we need to proceed to see what's going to happen if we complete our phase 1. So to solve phase 1, now is nothing but the simplex method. We enter x1 simply because x1 looks good. It has a positive coefficient. So we are good with that minimization problem. And then we do a ratio test. Okay, this is 3, this is 6. So x5 should leave the basis. And here immediately we know we're done. When x5 should leave the basis, x5 will become 0. And here x5 is our only artificial variable. So that means we will have a feasible solution for the original problem. Okay? And after we complete this iteration, we know x5 will never be used anymore. Whenever an artificial variable leaves the basis, there is really no reason to enter it again. So we can actually remove the column to save some calculations. Not really important, but you can do that. So after that, you only have 4 columns for the first 4 columns here, and the sum row operations will get you to the second tableau. This means the original LP is feasible, and a feasible basis has been found. It is x1 and x4. This is a feasible basis for your original LP. So now we should do the second phase, the phase 2. So we should first put the original objective function back. It was maximizing x1 plus x2, so we negate the coefficients and put -1 and -1 here. Again, before you start to run iterations, you see, okay, we say x1 and x4 are our basic columns, but this guy is not 0. So we need to fix the objective function again. So now we do the adjustment by adding constraint 1 into constraint 0, and then we get several candidates. If we enter x2, that means we want to maximize values, so we choose a negative reduced cost. And then we do pivoting once, and then there is still a candidate. We do pivoting twice, and then here we stop. Here we have a tableau with only positive reduced costs. That means there is no way to improve. And then we have an optimal basic feasible solution where x1 and x3, they are 6, and x2 and x4, they are 0. If we look at the graph, initially x1 and x2 are both 0. And then after one iteration in phase 1, we would move to 3, 0. Now please go back to double check. We move to 3, 0. That's the situation, that's the moment that we hit the feasible region. Okay, so x0 originally is infeasible, but then x1 is the initial basic feasible solution as a result of phase 1. And then we do one more iteration to get to the end of phase 2, which is an optimal solution. Still, we always move along edges. So after we get to phase 2, starting from our initial basic feasible solution, we move along edges to find an optimal solution. Here, all we are doing is to add phase 1 to move from an artificial feasible solution to the end of phase 1. If we can really cancel out or remove all those artificial variables, then we must be standing at a feasible point. Then we proceed. Or if we cannot, we conclude that LP is infeasible. Okay, so this is the end of our introduction of the simplex method. If this is the first time for you to learn it, seems to have a lot of materials, that's true. But if you think about it, well, nothing but searching among extreme points, searching among basic feasible solutions, if you are talking about standard forms. Nothing but moving along edges. Nothing but entering, leaving, ratio test, reduce cost, pivoting. And then you have tableau, unboundedness in feasibility, one phase, two phase, whatever. Go through them carefully and then you will learn everything. That's the end of today's lecture. Thank you.